This video is over chapter 20, orthogonality. So, in your notes, you have definition 215, which says what an orthogonal set is. So an orthogonal set of vectors is when you take two distinct vectors and you take their dot product, then you get 0. So this is a definition for Rn. And so one standard example is the standard unit vectors in Rn. If you take the dot product of two distinct vectors from this set, you have 0. Theorem 217 and Theorem 220, if you look at the proofs of those are kind of neat because it tells you what's nice about working with an orthogonal set of vectors sometimes. When you take the dot product of one with something that's not equal to it, you get 0. And so when we have these equations with orthogonal sets, sometimes when we play with them just right, we get a lot of zeros. And so a lot of things just cancel. And that happens in the proof of Theorem 217 and the proof of Theorem 220. I'm going to use Theorem 220, though, to do example 221. So Theorem 220 says if you start with an orthogonal set of vectors, it might be a basis, it might not be, but you start with an orthogonal set, and W is in the span of that set. So you can write W as a linear combination of these vectors. Then Theorem 220 tells us exactly what our coefficients are, C1, C2 through Cn. So the coefficient, the C sub 1, for example, is a dot product of W with V1 divided by the dot product of V1 with itself. The coefficient Ci in general is a dot product of W with Vi divided by the dot product of Vi with itself. And so this gives us a formula for finding the coefficients. So we'll use this to do example 221. We have a set of 3 vectors. And note that these 3 vectors do form an orthogonal set. If you take the dot product of V1 and V2, for example, you get 0. If you take the dot product of V1 with V3, you get 0. If you take the dot product of with V2 and V3, you get 0. This is an orthogonal set. According to Theorem 217, an orthogonal set is a linearly independent set. So by observing that this is an orthogonal set, we see that it's linearly independent. 3 linearly independent vectors in R3 span R3. So we know that the dimension of R3 is 3, so if you have 3 linearly independent vectors, they form a basis. That tells us that W can be written as a linear combination of V1, V2, and V3. So let's see how to do that using Theorem 221. So W dot V1, the dot product of W with V1, divided by the dot product of V1 with itself is what? Well, what's the dot product of W with V1? It's 1 plus 2 plus 3 divided by the dot product of V1 with itself, which is 1 plus 1 plus 1. Let's do the same thing with V2 and V3. The dot product of W with V2 is going to be 1 plus 0 minus 3. And the dot product of V2 with itself is 1 plus 0 plus 1. Finally, the dot product of W in V3 is going to be 1 minus 4 plus 3, which is 0, divided by, doesn't matter what the dot product of V3 with itself is, but let's calculate it. It's just going to be 1 plus 4 plus 1. this tells us what? That W is going to be 2 V1 minus 1 V2. And you can verify that for yourself. That W is 2V1 minus V2, well, plus 0 V3, but we don't have to write the 0 V3.